Hey everyone, and welcome to This Explainer. Today, we're diving into something really cool. We are going to completely demystify matrix algebra, drawing on some fantastic content put together by Santosh Sir. Now, if you've ever felt totally overwhelmed just staring down rows and columns of brackets and numbers, honestly, don't sweat it. We are not going to look at matrices as intimidating blocks of numbers today. Instead, we're going to treat them like an entirely different reality. I want you to imagine a world for a second. Picture a reality where the standard, everyday rules of math you've relied on for your entire life, the absolute fundamental truths of standard algebra, just suddenly fall apart. We're talking about a place where multiplication doesn't work the way you think it should, and where zero isn't quite what it seems. Spoiler alert, that is exactly what happens when we enter the universe of the Matrix. So, here's our quick roadmap for exploring this in your world. We'll start with Welcome to the Matrix, then look at the anatomy of a matrix, move into basic operations, navigate the multiplication maze, avoid some matrix algebra tropes, and finish up with a board exam survival guide. Okay, let's jump right into part 1. Welcome to the Matrix, the gateway. At its absolute core, a matrix is simply a rectangular grid. We always denote this entire grid using a big capital letter, like A, B, or C. And the individual numbers that actually live inside this grid, we call those its elements. I actually love the analogy from Santosh Sir's content here. It's kind of like a giant apartment building. The capital letters, the name on the front of the building, and the elements are the specific residents living in their strictly assigned rows and columns. Moving right along to part 2, Anatomy of a Matrix, Structure and Types. So, the absolute most important anatomical feature of any matrix is its order. And honestly, finding this is super easy. You simply take the number of rows and multiply it by the number of columns. So if we look at a matrix that has 2 rows and 3 columns, its order is neatly written out as 2 by 3. And if you want to know exactly how many elements are packed inside this apartment building, you just do the quick math. 2 times 3 gives you 6 total elements. Obviously, matrices come in a ton of different shapes and sizes. You've got row matrices with exactly 1 row, column matrices with 1 column, square matrices where the rows perfectly equal the columns, and diagonal matrices where only the diagonal has numbers. But out of all these types, you really need to notice the null matrix. Every single element inside it is a 0. It's an incredibly unique piece of this whole puzzle. But perhaps even more crucial is the identity matrix. You can basically think of this as the ones of this alternate universe. Its principal diagonal is entirely made up of ones, and literally every other element is a 0. For all intents and purposes, it's the matrix equivalent of the number 1. And it really sets the foundation for a lot of the complex math we're going to see a bit later. All right, part 3, basic matrix operations, the physics of this world. When it comes to adding or subtracting matrices, there is an incredibly uncompromising bouncer at the door, and his name is order. There is a very strict rule here. You can only add or subtract matrices if their dimensions are completely and perfectly identical. A 2 by 2 can only be added to another 2 by 2. If they match, boom, you're cleared to enter. You just perform straightforward element-wise math, combining the numbers in the exact same positions. Now, matrix addition behaves exactly like normal addition. It's commutative. Matrix A plus matrix B perfectly equals B plus A. But this brings us to our very first massive rule break in this universe. Matrix subtraction is strictly not commutative. A minus B definitely does not equal B minus A. You have got to keep your terms in the exact order they're given. Literally no exceptions. And that leads us to part 4, the multiplication maze, where the twist happens. Okay, before you even attempt to multiply 2 matrices together, you have to pass a really strict compatibility test. Think of them like puzzle pieces locking together. Step 1, look at the columns in your first matrix. Step 2, look at the rows in your second matrix. Step 3, they absolutely 100% must match. If matrix A has n columns, matrix B must have n rows. If they don't lock perfectly, multiplication is literally impossible. So, the crucial takeaway here is this massive departure from normal algebra. Because of that compatibility lock we just talked about, AB generally does not equal BA. In regular, everyday math, 3 times 4 is the exact same as 4 times 3. But in the matrix universe, multiplying matrix A by matrix B is a completely different beast from multiplying B by A. Often, doing it backwards isn't even structurally possible to calculate. And honestly, this brings us to a reality that is truly mind-bending. In standard math, it's a fundamental fact of life that if x times y equals 0, well then either x or y has to be 0, right? But check out this zero paradox. In matrix math, two completely non-zero matrices can actually collide, be multiplied together, and produce a totally null zero matrix. Neither A nor B is a zero matrix, yet their product is entirely zero. It's wild.
Let's look at Part 5, Matrix Algebra Traps, Board Exam Favorites.
So let's do a quick test of your survival instincts with a classic board exam favorite. Look at this equation. If matrix P times matrix Q equals matrix P times matrix R, can you just go ahead and blindly cancel out the P on both sides to conclude that Q equals R? What do you think, true or false? It is absolutely false. The cancellation trap is a major pitfall because you cannot simply divide out a matrix. In normal math, you'd cross out that P in a heartbeat, but here, the cancellation law strictly does not apply. Just because PQ equals PR, it does not imply that Q equals R. That is a huge trap to watch out for. Now let's see how this builds into another massive illusion, the standard squaring identity. We all had a plus b squared equals a squared plus 2ab plus b squared drilled into our heads. But look at the reality here. Because we just established that ab does not equal ba, you literally can never combine those middle terms into 2ab. The real answer expands into four distinct, uncombinable terms: a squared plus ab plus ba plus b squared. If you write 2ab out of habit on an exam, you are definitely going to lose points. Finally, Part 6, Board Exam Survival Guide, your main takeaways. Here is Santosh Sir's final exam checklist. First, we have the supremacy of square matrices. Remember, only square matrices can actually be squared or even have an identity matrix. And second, we have the absolute need to verify compatibility locks before you even think about multiplying. Do not trust your old algebra instincts. So, if you remember absolutely nothing else from this explainer, punch in these 3 golden rules. 1. To add or subtract, orders must match perfectly. 2. To multiply, columns of the first must equal rows of the second. And 3, never blindly use standard algebraic identities. Success in this universe really means actively unlearning your standard algebra habits. Ultimately, matrices force us to accept a broader, much wilder kind of logic. Just think about it. If two completely non-zero entities can combine to create a zero matrix, what other totally impossible-sounding rules are just waiting out there to be discovered as you dive deeper into higher math? Embracing this alternate universe changes the way you look at equations forever, doesn't it? Thanks for exploring this strange and awesome mathematical reality with me.